input the wind generation term was linear term, so it had no feedback of the short waves on the wave growth. So that's ST1. Yeah, so I'm going back to my slides now. Okay, so yeah, I'll talk about this framework business, the different source terms, a few things about the sea ice, and what we're still trying to do about the short waves. And you will find much more information about parameterizations. And I'll talk tomorrow about the coupled aspects. But yeah, most you will find in papers from 2010, Banner and Morrison, same year, and this Rascle and Arduin paper from 2 years ago. There's also a couple of papers from Babanin et al. And Rogers. Rogers and Babanin, maybe JPO 2 or 3 years ago. So yeah, again, so it's a framework. So it means that there's many options. And of course, the first time you try a model, as Henrik Tolman puts it, you use it out of purpose and probably in the wrong way. So you probably get the crazy results. So one good thing is probably to try to use the same settings as other people, but if you don't know why they're there, maybe it's not the optimal setting for you. So the idea of that is to try to make you understand a bit what all these settings do to the results. So all these general options are in this switch file. So that's a first general level of model adjustment. And this important thing, this choice of a switch, you do it before compiling, okay? And the reason for doing that is to minimize the size of the executable file, because it's running operationally for forecasting at NSET, so that has to be lean and mean. So the idea is that you don't want to compile one executable with all possible options in it. So it's like a preprocessor step. You just remove pieces of the code that won't be compiled. So this you do with choosing the switch. Now, once you have compiled the code, you have the opportunity to change some parameters, like some constants, like the coefficient for this or the coefficient for that. And this is done by name lists. And these name lists are defined when you generate the model configuration. And of course, the number of options and name list parameters just keeps growing. And we're now up to version 5.08 and get more and more options. So I don't have here the full list of the switches. You will find that in the manual. I know that many students have complained that the switch business is a big mess, because if you don't know what they are, you're completely lost. So maybe at some point we'll try to find a way to have some tool to do that a bit more cleanly. But now it's, yeah, so you have to know a bit about the switches. So I was talking to you first about this with generation anticipation. So this ST1 is this one cycle 3. ST2 is a parameterization from Tolman and Chalikov from 1996. ST3 is the parameterization from Peter Janssen with some recent updates. I think the default options of ST3, so the default name list values, probably correspond to the version of 2005 from Bidlow et al. So it's a report of SNWF. Or maybe it's more recent, but yeah. So it's possible to do normally the exact same source terms as SNWF if you want. You may just have to change a bit the parameters. ST4 is what we've developed here, essentially using some specific swell dissipation and then some dissipation based on the steepness of the local waves. I'll talk more about that. ST6 is similar in some ways, and maybe I can comment later on about that, but it's essentially the parameterization from the group from Swinburne University around Alex Babanin. And yeah, so that's the generation dissipation. Then there is a choice of propagation scheme. So you can go from no propagation, you just do a test, a simple test with a uniform motion, 1 point, you don't do propagations, just PR0. PR1 is a first order upwind scheme. First order means, of course, it's fairly diffusive, right? But it's steep. And you may be amazed to know that SNWF is still running the first order scheme on their operational forecast. It does a really good job for the wave heights. If you get the swells, you know, waves that travel long distances, and the wave packets is just, yeah, just diffuse everywhere, and the swell is not well resolved, and it was documented already 15 years ago, but yeah, the people in Europe, they don't care too much about the swells, not as much as the people in the US, and especially the Dutch. You know, they don't pay too much attention to the swells, so maybe that's the reason why SimDoLef is still running the first scheme. The other reason is that it's cheap. So there's always a compromise between accuracy and speed. And when you have an atmospheric model, which is called the wave model, like they have at SimDoLef, they only have 10% of the CPU time allowed for waves, and 90% is the atmosphere. And already with this constraint, they have to have a resolution of the wave model, which is not the same as the resolution of the atmosphere. And so they're always fighting in trying to make the wave model cheaper. So this choice of numerical scheme is also due to this kind of constraint. Another important source terms on the right-hand side of the wave action equation is the four-wave interaction four-wave interactions. That used to be the main cost of the wave model. I mean, back in the 80s, when the idea of a third generation model was introduced. So the idea of a third generation model compared to the previous generation models was that it had a specific, possibly accurate calculation of this very important process of four-wave nonlinear interactions. This process is what makes the shape of the wave spectrum in the WinC. It's responsible for driving of moving energy towards low frequencies and high frequencies, and it's a very important piece of the wave model. In those days, it has little computer power, and so I think in the one model, the cost of the model is half of it is still the DIA compared to the propagation and everything. So half of the CPU time is spent on computing this nonlinear interaction term. If you're using ST4, because we put more expensive stuff for the dissipation term, I think actually now the dissipation term is more expensive than the DIA. For the old timers, these people 60-year-old and more, it's crazy. You know, they want cannot make something so expensive. I mean, these days it's not such a problem, and we actually have more exact parameterization or computation of the DA. Actually, the NL2 is a full integral, the 3D integral of the exact solution. If you have a typical spectral resolution, NL2 will make your model about 100 times slower than NL1. So if you want to play with NL2, if you find it's very slow, don't worry, it's normal. It's just computing many integrals a lot of the time. There's been a lot of effort to try to find some solutions to compute this term very fast using neural networks, using diffusion approximations, many things. So very smart people have been working on that for the last 30 years. And there's still very little progress. Maybe the best alternative to the DIA these days is a multiple DIA in which we take into account different configuration of the resonant interactions. And some of that's been activated with NL3, in which you could have different things. The issue is that you have to tune some coefficients in NL3, just like there are coefficients in the DIA. So in the DIA, you have essentially only a few coefficients, maybe 2 or 3. In NL3, if you have 5 different nonlinear quadruplets, that number of coefficients can grow to 20, 30, and so then that is how to optimize that. So with WaveWatch, there is a genetic algorithm package to try to optimize that if you want to play. It's not a single block. So nonlinear actions is like most people, well, everybody for forecasting uses NL1, except for the Japanese that have something in between NL1 and NL3. Which is called the REAM, the Reduced Interaction Approximation. And it seems to be, they have pretty good results, especially around Hawaii on the peak period. So, I think there's some things to be explored there. Then there's some choice of bottom friction. It goes from BT0, which is no bottom friction. BT1 is a very old and strange parameterization, which was derived from the joint swap experiment. I say strange because in the data, when it was analyzed, it was said, well, okay, maybe we can have a linear dissipation term, but then the coefficient that you put in front has a variation of orders of magnitude based on that data set. And people just speak, okay, we're just going to take the median value of these 2 orders of magnitude and call that the gamma constant. And of course, it doesn't work all the time. And so what we've been working on, especially here, is to introduce the effect of the movable beds. You have sand grains, they move, they make ripples. And when you have ripples on the bottom, you have more roughness and more friction. And this is what is included in the BT4 parameterization, which is based on data from the SHOEX experiment. And we actually also validated here on the French coast. All right, so that was the more general short term. There's a lot of stuff about sea ice that has been put in the model. Some of these are dissipation effects with different rheology and different assumptions on the viscosity and the elasticity of the ice. I think right now we're running with IC2 and we're developing the IS2, which is a scattering term for having waves reflect in all directions with the sea ice. There's some reflection of the shore at the shoreline, which can be activated by setting the switch ref1. And you can also, and if you want to compute the second order wave spectrum, which can be used in the free infogravity waves parameterization at the shoreline, you have to use the ID1 switch. Then there's different methods for interpolating the forcing in space and time, and you will see all these switches, WNT0, KER0, and so forth. There's some switch for activating the NetDF4 libraries. And we also had some extra special switch for Anne-Claire to be able to run the model with time steps less than 1 second. Essentially, we just added one extra loop within the time integration. The funny reason is that the time in WaveWatch is defined in integer seconds. So, of course, if you have integer seconds, it takes a problem to go from a fraction of a second to the next fraction of a second. All right, so all these switches are repeated. So when you do the run and you post-process your output in NetCDF, you will find in the global attribute of your file the list of the switches. So you know the idea is that you can trace your model runs to the model settings. So that's done with the switches. We're hoping soon to be able to add all the nameless parameters also as global attributes to the NetCDF files, or maybe not all the nameless parameters, but at least the one that are not the default values, so that you know if you've done some changes, and you can see your file and you've done the change. And yeah, so there's not two people that actually run WaveWatch in the same way. You know, maybe in your case, you may want to change the configuration because you have some special needs. So don't want to worry too much about it. The first thing to do is probably to adjust the forcing field parameter, the forcing parameters, essentially the ST2 or ST4, ST3, whatever you want to run, to the same values that are used with the same winds. So, for example, when we're running with ECF winds, we have one set of values for the coefficients. If we run with the NCEP winds, we have another set of values because these winds are, you know, they give the same patterns, but they have differences. And we have when you have a difference of 10% in wind speed, you can have a difference in 15, 20% the wave height. So it's a big difference. I mean, these days we're chasing biases in the wave models of a few percent, 3, 4%. So 5% is, yes, it's too big for us. So we have to adjust, either you adjust the winds before, or what we actually do these days is mostly to adjust the wind wave growth parameter. So in ST4, we essentially play with the beta max coefficients, and that's listed in a manual. You'll find the table with all the coefficients for the different type of wind fields. We just had an email from a colleague in Australia last week telling us that, well, there's a new high-resolution forecast and analysis from NCEP. They're going out 1/4 degree global, and the analysis is 1/8 of a degree. And he was asking us if we already had some tuning coefficient for these, and the answer is no. So we probably will try to play with that and see if we need to adjust or not the parameters to the new NCEP resolution. And so the impact of, you know, for example, going from ST2 to ST4 switch, this is what had happened at NCEP in 2012, so a couple of years ago. So we are part of this a big US project as part of the National Ocean Partnership Program, the NOP, to put in the version of WaveWatch all the research that we've done and improve things. And as a result of that, NCEP took that for their operational system. And this is a map of the bias against the altimeters. This figure was done by Arun Kaulas. This is with the ST2, this is with ST4. And you can see that the bias is quite a bit reduced. There are some regions of low biases on the East Coast, and we know that. So we have a problem there. It's a bit positive on the West Coast. We're talking about 10 centimeters. So here, there's a bit too much swell. We have some problems with swell dissipation. And here, the wind sea growth at short fetch is still a bit too slow. It's also the reason you don't have the Mediterranean in that case, but if you run the same parameters on the MED, you will see that in coastal areas, it's a bit too slow. But the idea is to have something that runs globally with the same parameters everywhere. So it's working more or less okay. You have some red blobs here and there. Some of these actually are not the problem of the wave models, or not only it's because there's icebergs in the ocean, and the icebergs have a big impact on the wave because they just like breakwaters. The waves just crash on the iceberg and don't go past it. So we actually also have a parameterization for the iceberg effect, and we also have a database of icebergs. You can talk to Mikhail about it if you're interested in the Southern Ocean. And that's so these are 1 year of biases against NVSAT JSON 1 and JSON 2. So it went from a positive bias of about 25 centimeters to around 0, except October. And the scatter index was a big reduction in errors, RMS errors, and error squares. So NCEP was really happy about it. And this has been running at NCEP since 3 years now. The people on the West Coast were super happy because the swell was great. The people on the East Coast complained a bit because, yes, short fetch behavior, northeasters were not so good. So part of our work here on trying to improve the short waves and the tail of the spectrum is also driven by this issue of the short fetch behavior. Because if you change the tail, you're going to change the wind stress. And then if you change the wind stress, that's going to change the growth for the entire spectrum. And this comparison here is ST3 compared to ST4. So same wind, same everything, just going from ST3 to ST4. This is the version of ST3 that corresponds to below 2005, and that was run at East-Andref until 2005. They had some problem with the swells in the Pacific. Essentially, they didn't have enough dissipation for the swell, and so the waves were accumulating as it traveled across the Pacific. You had too much waves in that region. So now they retuned things a bit. They essentially reduced the generation in the storms and increased a bit the swell dissipation. So now they have a low bias in the high latitude and almost no bias in the tropics. But if you look at the spectral shape, then you see that swell dissipation is still a problem. And so the big difference in going from there to that is, first of all, that what was introduced in the source terms, especially the dissipation term, is the idea that the wave dissipation is not a function of the steepness of all the waves. In particular, if you have some long waves, they shouldn't have a big impact on the very short waves. And that was shown from measurements by Banner et al. And the first was used in some parameterization by Albert et al., but that parameterization had some other issues. And one of the difficulties that was 10 years ago is that, okay, so we started to have a good dissipation for the short waves, but what about the swell? And so one of our big work here was to actually measure the swell dissipation across the oceans thanks to the SAR data from NVSAT. So now we could separate cleanly the swell dissipation from the wind speed dissipation. We have some hypotheses of why there is swell dissipation. There's still a big debate whether it is due to turbulence in the water or friction in the air. So the jury is still out. But the parameterization seems to be doing a good job, and still there are some biases that we still don't have enough dissipation when we tune things. And so we have a couple of people working here on this question. And so, yeah, so this thing here now is operational at Météo France, NOAA-NCEP. I think Environnement Canada also has been using it now. Yeah, as you can see, there are some red regions here. Some of that is due to resolution. It's a half-degree global model, so you don't expect miracles in the MED. But still, there's problems at short fetch. And if you take a bit longer time perspective, it's like these 4 parameterizations, so ST1, ST2, ST3, ST4. That's the typical maps you have for biases and normalized RMS errors. So again, low bias is blue, purple. High bias is red, and here red is high errors and low errors is blue. And yeah, in the trade winds these days, so this is for a couple of years ago. But for the forecast now, or rather the analysis now in the trade winds, yeah, the errors is typically less than 7%. It's amazing. The winds are very steady. I think that's the main reason. The winds are highly predictable. Some of these errors also come from the wind field errors because this is based on analysis winds. Yeah. Ah. Yeah. It's this is related to our east versus west issues, and it's essentially long waves and short stretch. So I think this is why we still have some big errors here. The big errors that you had here in this, I will explain right now. This is because in the SC3, the dissipation rate is based on the mean steepness, which is defined from the entire spectrum. And okay, maybe I can jump to that because mean square slopes is okay. Mean steepness. All right, so this is what in the early days of the wave models, trying to find a way to represent the effect of wave breaking. It's you don't see it so well now, but you pretty much define. Imagine you have foam. It's a two-phase flow. It's physically it's a mess. So it's, wave breaking is a very complicated thing, and trying to summarize that, and especially to give the distribution of dissipation for short waves, long waves, and everything, different directions. We don't have a good theory for that. So there was a lot of argument about, okay, so it has to be a quasi-linear term, because if you take a little bit of energy from the spectrum, it's not going to change everything, blah, blah, blah. Okay. And so at some point, people say, well, it has to be rated to some steepness effect. If the waves are steeper, they're going to break more. Right, makes sense. And what was introduced by Klaus Hasselmann in 1978, and it was used in the one model in the first version, 1.3 and 4, is to essentially take the spectrum, you multiply it by some wave number to power r, and that will define a mean wave number, like we had yesterday, the mean period. And what they cooked up for the dissipation term was some coefficient times this steepness. So k times wave height is steepness, okay, because it's the wavelengths, or in other words, this is a height divided by the wavelengths, right? Because k is 2 pi by the wavelength. So h times k is 2 pi times the steepness. So this is a steepness coefficient, and this is in front, and this is the same parameter for the entire spectrum. So you have all this stuff is multiplied by the spectrum. And then they realized that, so in 1.3, they only had this term, which was k over some mean wave number. And then in 1.4, they started to have a different wind input term with more input towards high frequency. So they had to balance that. So you need to have a stronger dissipation at high frequencies. And so this is why they introduced this k-squared term. This is what Peter Janssen took 1 year to play with that and thought, okay, I'm going to put some k-squared and some coefficients. Okay, that's so if you imagine the spectrum with the low frequencies and the high frequencies, this mean wave number is somewhere in the middle, right? And but the issue is that if in the C state, if the C state grows or if you add some swell, essentially you're going to add some energy at low frequencies. You move this mean wave number towards low frequencies, and then that will essentially, because of this parameterization, this will make this term much bigger. The k-squared of a kr, if you reduce this becomes much bigger. And so that happens, so the kr will become smaller if you add some energy at low frequencies of the spectrum, will put more weight towards low frequencies, and so the whole equilibrium will be cancelled, and the small ball will now feel like an elephant, and you get a tail which will be heavily dissipated. So that's what happens. And when you're looking at East Coast in the open ocean, you do have swells once in a while coming in, not so often as on the West Coast. And as a result, there's a lot of noise which is introduced by the swells at parameterization. And actually, in reality, we know that swells, yes, can reduce a bit the level of the short waves, but not as much as what the parameterization gives. So this was really a big problem of the parameterization. If you go to the extreme, well, it's still realistic. You take a very long swells, 20 seconds of a wave and a height of 2 meters. You start from the swell, the wind sea, and you blow the wind. And you look at the growth of the wind sea from time equals 0, and you integrate that. And so I did that actually running the Etienne-Dolef code, this cycle 38R1, which is a version of 2 years ago. And I did that with or without the swell, so just WinC or the WinC with the swell. And if you, so essentially these are two slightly different adjusted versions of the WAM cycle 4 models. One is from the paper 25, and this is from a couple of years later. Without the swell, you get the usual WinC growth. Okay, so it goes up like that, and after 10 hours, you get up to something like 7 meters. If you have some swell, initially you have the weight of the elephant, and the weight of the elephant is preventing the short waves to grow and to make some roughness and to let the wave develop. And this is completely unrealistic. Nobody has ever seen an effect like that. At short fetch, the WinC should grow, and it's not some crazy effect like that. So of course, Jean Pilot hates when I show this plot, the colleague from ECMWF, but this is what this model gives. Okay, so that was the main motivation for going away from this mean steepness. And so what we've done is to go to the other extreme, which I don't like too much either, but it appears to be a bit better. So instead of saying that, okay, the dissipation is going to be a function of the steepness of all those waves together, now we're going to say that, okay, we'll take some waves, and at one region of the spectrum, we're going to look at the steepness of these waves, and that will define the dissipation. And the difficulty you have in doing this is that the easy shortcut is to say, okay, I'm going to look at the energy at one frequency, and from that energy at one frequency, I'm going to say the dissipation rate is that much. Well, if you have very fine spectral resolution, and you imagine you have a monochromatic wave with delta diffraction distribution, the spectral density is infinite, and so even if a gentle swell, you would say that the dissipation rate is very high because you have a very high spectral density. So it makes no sense. So you have to integrate the spectrum over some bandwidths to define the energy in a given scale of waves, and from that you get the dissipation. Now, integration means more CPU computations, and this is where you start to have the compromise between some parameterization, which makes more sense, and the cost of it. And in the end, right now, what we're doing with ST4, we have two options. One is to integrate in frequencies, the other one is to integrate in directions. Ideally, we should do both, but it's just too expensive. So there's some shortcuts, and in the end, we don't have so much this effect of the swell on the WinC, and I think this was supposed to illustrate that. These some measured cases from 2007 in which you have swell peak and a WinC peak. The squares here is this ST4, and the symbols here is from ST3, I think. Yes and no. Well, yeah, whatever. So you can go back to that paper and you will see that when you put the swell, ST3 has a big impact on the dissipation and it's not realistic. And in ST4, when you put the swell, it has no impact or very little on the WinC growth. And so I had some other, and I had some other things. So that was the swell and the WinC. One of the side effects of this story on the slide number 11 here is if you look at the tail of the spectrum, and very few people actually looked at that before, and you compute something which is a spectrum times f to the power 4. So that will give you the fourth moment, and from that you take this m4, blah, blah, blah. That's give you the mean square slope. So it's like integration of the spectrum times k squared. So k times the height is the slope. K squared times the spectrum is slope squared, and you integrate that to get the variance of the slope. And this parameter varies with, I think I told that yesterday already, with the wind speed, and for each wind speed, it varies with the wave height. This is from radar altimeter data, because the strength of the backscatter is roughly proportional to the inverse of mean square slope. So if you have a flat sea surface, you get a strong backscatter. If you have a rough sea surface, you have a weaker backscatter, and the proper coefficient is a mean square slope. That's the observations. This is what we do in the model. So it's kind of okay for the low winds. At high winds, there's still some issues. And this is what the ECMWF model gives. First of all, the average is not in the right place. But then for given wind speed, the mean square slope actually decreases because of the elephant. And the tail is too low in the EWF models when the waves get more developed. And so we've used this kind of data to try to find the right balance between the dissipation term and the input term. This is a early failed attempt. So it was okay for the low winds, but not so good for the high winds. And the difference between this thing and that thing here comes from what we call, there's a sheltering effect that we had to introduce to reduce this input for the high frequency waves. So we have one general formulation for the input that we took from the 1 cycle 4 from Peter Janssen, but we could never get a balance at high frequencies with that. So we said, okay, well, we'll have to reduce the high frequency generation, and that was done by introducing this sheltering term. So in the wave-watch parameter list, you will see some parameter called something shelter, and the default in ST4, the value I think is equal to 1. And if you don't put that in, then the tail will get crazy, especially at high winds. Now, the problem of this sheltering term is that it killed a nice feature of the WAM parameterization, which is the fact that the U star, so the wind stress, was a strong function of the wave age. And that's very important when you're coupling the atmosphere to the waves. And actually, that's the reason why there's still a pretty important wave group at ECMWF, is that because they have a coupled wave atmosphere system, the changes in the roughness of the ocean is actually very important for the forecast of the atmosphere. And so we're still discussing this with Jean Bidlot, and actually I was supposed to work on this, but fortunately Lucia is going to take this up to look at the impact of parameterization on the atmosphere. And what's possible is that if we actually plug ST4 inside of ECMWF code, which is actually what is run by Météo France today, maybe the atmosphere forecast is going to be worse. Maybe it's going to be better, or maybe we have to find something in between. So the issue is how we compute the wind stress from the waves. And right now, so the 1 cycle 4 parameterization was designed for that. And the changes that we've done to improve the waves, it seems that for the wind stress, it's not better. So there's still some work to be done in that area. And there's some of that is also done in ST6, but in ST6 they've chosen to actually fix the drag coefficient as a function of the wind speed, so they have absolutely no wave age dependence in the parameterization. So that's about the status of where we are. And this last slide with different parameters and parameterizations that was especially for the seismic noise people is an example of different model results. So STC here is ST2, this one is ST3, and this one above here is ST4. And this was to illustrate the value of, that's the spectral density of the overlap integral, which goes into the seismic noise source. And this is a scale in dB. So the average here is maybe 40 dB. Here it's minus 20. So there's 20 dB difference between EC and ST2 and ST4. And it's hard to get an absolute calibration of that, but the relative changes should be compared to the measurements here in red. And even the variation is not very good, and that's what's happening at 1 hertz. So at 1 hertz, acoustic frequency, which corresponds to waves of half the frequency, which is 0.5 hertz, the wave directional spectrum is really bad. So don't expect miracles. The mean direction will be just the wind direction, so it's okay. But the distribution of energy at high frequencies is a real problem when you go beyond 0.4 hertz, especially in the global ocean. So that we have a PhD student working on this at Charles Perreux, and so hopefully he's going to come up with some ways to improve that. What we're introducing in parameterization these days is, first of all, a new term to make some short waves, some large breaking waves. So like large breaking is going to splash and make some short waves in all directions. We're also looking at ways to reduce the energy in the wind direction, because it's a bit too high now. And that could be the effect of modulation of short wave by long wave, and also the effect of the shear of the current, which causes some instability and makes the wave break more easily. And all these things are not parameterized in the model now. So If you actually look in the code in ST4, you will see some of these things. They're not yet in the manual because we're still playing with them, but hopefully it's going to work soon. And this is just to illustrate the directional distribution at different frequencies with ST2, ST3, and ST4. And you see that here it's more a sharp angle here towards so there's almost no energy going perpendicular to the wind, and here you actually have more energy that's almost perpendicular to the wind direction. So at the peak, so it's in black, it's at the peak frequency, so it's more or less the same, but at high frequency you will see that ST4 has a much broader directional distribution than ST2, and this is actually more realistic when you look at directional spreading, but it's still not broad enough at about 2 or 3 times FP. Swell, yeah, that's much better. Swell, I'll skip that. The elephant, I did talk about it already. Breaking, yes. Yes, I talked to you about this, the sheltering term, and the difference. So these are source terms. Sorry, these are spectra of the wave model, and to have them go flat at high frequency, they have been multiplied by f to the power 5. Typically, the spectrum at high frequency from the observation should decay like f to the minus 5. And so if you multiply by f to the power 5, you're essentially looking at deviation from this saturation level. So the reason for f minus 5 has been explained by the fact that at high frequencies, the wave breaking becomes very important. And the idea is that the shape of the wave is limited by some maximum steepness. Essentially for monochromatic waves, it's 120 degrees sharp corner from the Stokes maximum height. And if all the waves have the same steepness, then it means that the wave number spectrum, so all the scales should look the same. So the wave number spectrum, non-dimensional spectrum, should be flat, and the non-dimensional spectrum actually corresponds to this parameter V0, which is the spectrum times f to the power 5. So the reason why it's flat is expected to be due to dissipation, and with ST4 and with ST6 also. It kind of works. It's more or less correct up to 0.4 hertz, but it's still growing. So it means that it's not decaying f minus 5. It is decaying more like f to the power 4.5. So we're trying to fix that. So some of the ingredients. So one of these ingredients was a sheltering term. Okay. The other one is a cumulative effect, which essentially is saying that the dissipation is not just a local effect in the spectrum. So the short waves dissipate also because there are some long waves that are breaking or something is happening with the long waves. And how you parameterize that in detail is, So there's also a group with Ken Melville that has something a bit different. And I tried what they use, and I don't quite get a f minus 5 level. So this is still work going on. And so, right, so because the tail was really too high, and I was afraid that people would use the model result and say, well, this is crazy. So I finally dug in and said, okay, I'm going to put back what is used in WAM is to actually impose that the tail at high frequency goes like f to minus 5. So we had a debate with some colleagues about whether that was better or not. So that's a map of RMS errors with a new model with including that. And so this flavor of the ST4 is called test 471. The one without this tail forced to MS5 is called test 451. And so now it's a bit better at short fetch, but with it's still a temporary fix. And the default version of ST4 is still S451, in which the tail will probably grow too high at high frequencies. So if you stop the model at 0.5 hertz, 0.7 hertz, it's more or less okay. If you actually go to like 2 hertz, then it's going to be crazy. So be careful about that. The tail is still a problem. And so one quick fix is to impose in the code that the tail should decrease like f minus 5. But I don't like that. Okay. And this is just to show you that, I mean, on average, the models give very good results. But you just look at simple conditions, the growth can actually be fairly different. This is, in red, is the growth curve from the WAM model. In green, it is the one from the ST4 So essentially, this is ST3, this is ST4. And when we started implementing that in the WAM model at ECMWF, yeah, Jean Bidlot got scared about it. It's very different. It's just different. And yeah, what you see is that the growth. So initially, the WAM stuff grows very fast, and that is because of the feedback of the short wave through the wind stress that makes the wave growth faster for the dominant waves. So this is where it's probably a bit more realistic because there is this short wave enhancement of the wind stress. Right. But when you look at the overall results and you compare buoy data and look at the scores, there's this what we do every month. Well, this is what Jean Bidlot is doing every month. So we send him the data and all this like 10 different centers from ECMWF, the UK Met Office, Météo France, this is our model, the Danish Met Office, NTN, I don't remember who that is, but you have the cluster index as a function of the forecast range. So 0 is the analysis, 1 is a one-day forecast, 2 is a two-day forecast. This is for buoys in the Southern North Sea, and you can see that, well, we're actually getting better results than ECMWF, especially on the mean periods. But so that was a couple of years ago. And they improved their stuff recently, so I'm a bit upset. So these days, ECMWF is looking a bit better globally, not so necessarily on the coastal areas. Of course, they have wind speeds every 10 minutes. We're using their winds offline every 3 hours and blah, blah, blah. And so there's many different things. And when you actually run the ECMWF model without that simulation, the models are actually clearly not as good as what we can do with our new parameterization. But these are the numbers, and you can see that, for example, for all the buoys around the world, the RMS errors on wave height grows in time. So initially, all the models which are driven by the same wind, so Météo France, ECMWF in red, and our model here are using the same winds. Météo France and ECMWF are assimilating altimeter data, so they get a better analysis. But in the long run, we actually get better forecast, and I think that's thanks to the better numerical schemes. But also thanks to the better parameterization for the wave dissipation. So that's the wave height, and that's even more clear for the peak period and the mean period. So here, that's the Météo France forecast is actually giving you the best peak periods globally. But 1 month and the next month can change a bit, but these models give similar results. And that's for the Med. So yeah, we have a big difference in the Mediterranean, especially on the mean period. So this is our model, Météo France, and ECMWF. But in some other places like Gulf of Mexico, ECMWF is better because of the short fetch features. Any questions? Yes, in general. Yeah, so for short fetch, actually what we do, we have a special tuning for the Mediterranean. And I think it's in the manual, it's 405. So in the Med, we actually run with different settings than we run in the global ocean. And yeah, otherwise, yeah, if you look at each buoy from the global model, yeah, ECMWF is doing a better job because I think it's really related a lot to their the way the winds, the wind input, so the generation term is a function of the wave age. And so there is this feedback of there's a feedback of the short waves to the wave growth for the dominant waves. And it's something that we killed to get the balance in the high frequency tail, but it's also having a bad effect on the short fetch. And the big difference between ST1, so 1.3 and 1.4 was actually this introduction of the wave age dependence on the U star, which improves a lot the forecast, especially in the North Sea and all the small basins. Okay, if you're just doing the Gulf of Mexico, you don't care about boundary conditions. Just make it a bit bigger, and then the hurricane will just make waves when they pass by. But there's not much that actually goes through the Yucatan Peninsula, and so people usually actually include the Caribbean and the Gulf of Mexico in the same run. It's maybe easier than having to go through the. Yeah. Yeah. Yeah, you can use different pronunciation, or you can use ST4 with slightly different tuning. And actually, in the paper, 2010 paper, we have a test case from Hurricane Ivan, and it's right on. So I think for the big hurricanes, it's not such a big problem. It's more for the northeaster with more moderate winds. But it's all a function of which wind products you use. If you use the H winds from the Hurricane Center Miami or the GFS winds, or you're gonna get different results. So there will always be some tuning with the winds, whatever parameterization you use. So if people are using the same winds as you, and you can just use their parameterization, but if you're using a new different source of wind, then maybe it's good to test and possibly play with the wind wave growth coefficient. So in ST4, it's called beta max, and also in ST3. In ST6 is some other coefficient, but if you just look at the chapter 2 of the manual, you'll see the equations and the name lists. Time for the break, yeah.